Hi there, and thank you for joining me. Welcome to this webinar on flow simulation for optimizing medical product design. My name's Matthew Fordham, and what we're going to do today is have a look at how we can use SolidWorks Flow Simulation to try and drive our designs and to try and optimize how we design things before we have to make anything. Before we get started, I have got a question here that I thought it might be handy to answer before we get going. So thank you for this question. The question is, I haven't done any CFD before. Do I need much prior knowledge? And there's a very, very simple answer to that, and that is no. Flow simulation in SolidWorks is geared towards the designer. It's a tool that's been refined so that you don't need to be a simulation or a CFD specialist to use it. It's ideal for those of us that are trying to design and just want to try and optimize our designs before we start having prototypes made, or even before we send it to a specialist for a full simulation. And what it allows us to do is quickly analyze our designs and make sure that they are coming out as we want. So hopefully that's that question answered. If you wanted to discuss that a little bit further, please feel free to submit another question at the end and we'll carry on. So without further ado, let's jump over and start having a look at our model. So what we've got here is a very simple system. I've got two tubes which are serving as inlets here, and I've got a one single outlet. So ideally what we're looking at here is mixing two different fluids. So we've got a water inlet here and an ethanol inlet here. And we want those two fluids to mix well, so that when they reach this body here that I've stuck in, which is going to represent our sensor. So perhaps we're designing the entire system, perhaps we're just designing the sensor, who knows. But in this case, what we want is for the fluids to be completely mixed at that location, so that the sensor is getting an accurate reading of the mass fractions of the ethanol and the water. And then the fluid is just going to continue out to atmospheric pressure at the outlet. So let's jump in and have a look at setting up our study. You'll see I've got a flow simulation tab up the top here, and that really is a sign of how easily flow simulation integrates with our SolidWorks standard user interface. If I select the wizard here, we jump in and start creating our study. So first of all, we're going to choose what configuration we're going to use. You'll see later that I've got a number of configurations that I'm going to run the study on and try and optimize my design, and therefore I'm going to insert the study into the same configuration that I'm in now. We could, by all means, if we wanted to run a number of different studies on the same thing, we can just keep generating new configurations from here, giving it a name and attaching a new study to each of those configurations. In this case, we're just going to use current. Okay, next, the system asks us to specify our unit system. So here we can use we're going to use the standard SI system, but we could by all means use any of the others you see in the list here. For example, our friends across the pond might use the USA unit set, which is essentially just all imperial values. We're not going to do that, we're going to stick with the SI units. Okay. So next we come through to select our analysis types. This is where we start setting up our study parameters. So first of all, we know we've got an internal study here because we've got a closed off set of pipes, and we're studying the fluid flow inside those pipes. By all means, if we wanted to conduct an external analysis, so for example, we could study the exact same thing but have air blowing past the outside of the tube, we would select external analysis. We could still close off this volume and have an internal flow inside an external analysis. Next, we select how we're going to consider our flow cavities. So for example, if the sensor that we've got in there was hollow, we would have a cavity inside, and we might not have flow conditions. Well, chances are we won't have flow conditions set up for inside that cavity, and we can select from here to exclude that flow condition, and that'll simplify the solve a little bit. Next, we come through to select our physical features or our flow phenomena that we want to include. So first of all, we've got heat conduction in solids, And what that's going to do is allow us to analyse how heat is conducting between the solids that we've got in our system. If I select that, you'll notice we also get the option to solely conduct heat through the solids and not analyse the flow. So that's very, very similar to the thermal analysis tool that we've got in the standard SolidWorks simulation tools. We also have the option here to include radiation, so that is, say, black body radiation, so that's thermal heat transfer without a medium, in the same way that infrared light is taking energy from the sun, and we can still feel that heat even though there is a vacuum in space. Very, very similar. We can include that phenomena here. Next, we've got time dependency, so we can select this box if we want to conduct what's commonly referred to as a transient analysis. So here our results are entirely dependent on time. So what we can do is set the study up to analyse different flow structures and how they vary with respect to time. So we might have a study that is shedding vortices, and these vortices will be alternating or something like that. And if we conduct an equilibrated or a normal flow analysis, these structures will become a blur because the results will be averaged so that we have a convergence. Whereas with a time-dependent study, we can see how those structures move downstream with respect to time. Here we've got gravity, and I'm actually going to check that because we're going to use that in this case. It's fairly self-explanatory. All we need to do is make sure that we're specifying the direction. So I'm just going to check with my coordinate system icon down the bottom here, and my gravity is in the negative y direction, so minus 9.81 meters a second squared in the y direction is absolutely fine. We'll leave that as it is. And then finally we can include rotation, and rotation allows us to specify an entire or a section of the computational domain to be rotating, and this allows us to analyse, for example, fans or turbines and this sort of thing, where ideally the component is rotating or moving, but we don't have the ability to analyse moving meshes in flow simulation. So instead we can move our coordinate system and gather a similar result, and that's what that tool does for us there. Okay, next we need to specify our fluids. So we've got a number of fluids here. Everyone is fairly Everyone is fairly used to referring fluids as liquids, whereas in actual fact a fluid is simply a medium, a flowing medium. So here our fluid could be a gas. So we've got a wide range of materials here in our database. Of gases, liquids, we've got non-Newtonian liquids, so these are thick viscous liquids or liquids that don't follow a linear pattern, so for example blood, applesauce, there's a couple of weird ones in there. Compressible liquids, we've got compressible water here, real gases, so refrigerants, carbon monoxide, etc., and steam. And we do always have the opportunity to add new ones if we want, so we can come in and we know the values or the properties of these fluids, so we can add our own ones in there. For this case we are going to use ethanol and we're going to use water, so I'm bringing those in simply by double clicking them. And down the bottom here you'll see we can specify a flow type, so we've got either laminar or turbulent at the moment, so this allows the system to determine separation or transition between a laminar flow and a turbulent flow. We can also drive the flow to be solely laminar or solely turbulent. We're going to leave that at laminar and turbulent. Next we move on to our wall conditions. So here we're specifying first of all the wall thermal condition. So at the moment it's adiabatic, which means that there is no heat transfer at the wall. We can also specify heat flux or heat transfer rate, so that's a rate of heat going into the fluid from the wall, or we can specify a wall temperature, so that would have a similar effect but with different properties specified at the beginning. And then finally we've got the roughness value, and this is just a value which determines how much interference or how much turbulence is generated due to roughness of the wall. We've got a clear plastic tube. We're expecting that to be pretty smooth, so we're going to leave that as 0 in this case. And then finally we've got our initial conditions. So the initial conditions are values that we can stick in to aid the system in its solve. So for example, if I know that the fluid by the end of the simulation is going to be moving in the Z direction at about 2 meters a second, if I put that in here, the fluid will start off moving at that speed, and then that will allow the system to converge upon the final result a lot quicker, because we're already in the right sort of ballpark. I don't know anything about my flow in this case, so I'm going to leave all of these values at defaults. And then finally we've got the mesh. So after we've set up all of our parameters, so that's our flow situation, we've now got the mesh. Now for those of you that have got any sort of computation analysis experience, so CFD or FEA, you'll know that meshing is a vital part of the process, and in actual fact it's one of the biggest driving points of the accuracy of your results. We've got a number of tools available to us in the meshing environment. Here we've solely got a slider, which makes it really easy to either go to a really fine or a really coarse mesh. So let's make that at the default at the time being, or we can come in and start specifying specific values, so we can use numbers to drive the size of our mesh if we are starting to get a bit more advanced and get to know the meshing tool a bit better. This is a fairly automatic environment. We'll come back to the manual process in a minute, and for the time being you'll see now that we've got an extra icon at the top of our property manager, and here we've got the flow simulation tree. So you'll see now our computational domain is displayed on the screen, and we can start adding our boundary conditions. Now boundary conditions are our inlet conditions or our outlet conditions, so this is where the flow enters or exits the system. And for that we do need an area in which we can specify our boundary conditions. We also need a way of closing off our volume so there is actually an internal flow. Notice it is solely a tube at the moment and we can see all the way through it. So what we're going to do is generate some lids. Now there is a handy lids tool in the flow simulation package which allows us to come in and simply grab each of these faces, and the system will automatically specify or add a lid in there, and that's just a solid body that's placed inside the assembly. For this case I've already generated some previously, so I'm just going to unsuppress those, and it'll ask me to update the mesh, and there you go. So now we can see I've got a lid there that's closing off my volume. So right click on the boundary conditions now, I can select the internal face of that lid, which is where the fluid is going to interact, and start bringing in some of my values. So I'm going to have an inlet mass flow rate of 0.001 kilograms a second, so that's a gram a second essentially of water, and we do need to make sure that we are specifying, so I'm going to specify a mass fraction of water to be 1, so that's an entirely water inlet, and I'm going to select OK, and that's boundary conditions set up. Next I'm going to do a similar thing for the ethanol inlet, so I'm just going to grab that internal face again. I'm going to leave this value at 0.0001 kilograms a second this time, so that's 0.1 grams a second, so we've got more water than ethanol coming in, and I'm going to specify a mass fraction in favour of the ethanol this time, so we've got entirely ethanol at this inlet. Finally we just need to specify the boundary condition on the outlet, so I'm just going to select again the internal face of that lid. I'm just going to specify environmental pressure, so these are the ambient pressure conditions at that outlet. Okay, that's my flow regime set up, so there isn't much else to do before we click run. One thing that's always handy to do is set up our goals. Now goals are what the system uses to guide its convergence. So when we talk of convergence, that's reaching a steady state result, if you will. CFD in its nature isn't a finite thing, it's a perpetual solve which will carry on until you tell it to stop, in effect. So what we need to do is find ways of telling the system when to stop. There's a couple of ways. We can specify a maximum number of iterations, so we can say show me the results, give them back to me after 1,000 iterations. We can say you're allowed to solve for an hour and a half and then I want the results. Or we can use some convergence goals. So if I right click on the goals, I'm going to generate some global goals here, and in this case I'm just going to select the average and the maximum velocities present within the entire control volume. So if I select OK, you'll see that these two goals are generated. Next, I'm also going to have a couple of goals just to verify that we've got the correct mass flows on each of the inlets and outlets. So in this case I'm going to generate some surface goals, and I can actually expand another tab of the flow simulation tree, which allows me to select all of these boundary conditions, and what I'll do is pick up that internal face that we used to specify that boundary condition, and then I'm just going to select the mass flow rate there and ask SolidWorks to generate a separate goal for each of those selections. So now we've got mass flow rate 1, 2 and 3. One final thing I'm going to do is generate another goal called an equation goal, and I'm going to use this goal to sort of verify mass continuity. So I'm going to grab that outlet mass flow rate, and from that I'm going to subtract the summation of the other two mass flow rates. So essentially we're ensuring that the mass flow rate in equals the mass flow rate out. So ideally we want that equation goal to be converging to a value of 0. And that's about it. That's our study set up. One thing I'll do before we move on is come back to that mesh. Like we said, there are some more manual tools available to us. So what I'm going to do here is stick in some of my own values that once I've got to grips with the software a bit more, I can start doing this sort of thing myself. So I'm going to bring the small solid features refinement up to 4. So small solid features are features that are solid and significantly smaller than the computational domain. So for example, our sensor here is significantly smaller, and hence what this is going to do is refine the mesh around the area which surrounds that sensor. I'm going to bring up the curvature refinement, which is just going to ensure that all of the mesh elements are capable of reflecting the curvature that we've got inside the tube. Obviously we've got curved walls, so we want to make sure the mesh is fine enough for that. And I'm just going to bring up the values on the fluid and the partial cells. So the fluid cells are obviously all of the cells that are entirely in the fluid, and the partial cells are the cells that are running along the boundary between fluid and solids. So these are the cells that make up our fluid boundaries, if you will. And then I'm going to select OK, and that's our study pretty much set up. So what I'm next going to do is have a look at some results. So I've already set this study up beforehand, and I've got some results. So I'm just going to load those in. And what you'll see here is I've got exactly the same setup, but I've changed the names of each of those items just so that we can see that it is set up exactly the same as it was before. And now let's start having a look at our actual results. So first of all, we'll have a look at our mesh. We'll see how that was generated. So I'm just going to select the mesh icon from our cut plots, and I'm going to use that right plane to cut the geometry. So when I hit OK, what you'll see is we get display on that plane of our mesh. So you'll see that along this boundary we've got much finer elements there, and likewise around our small solid feature, as we mentioned before. You'll also see how the mesh has been refined around this curvature region. Okay, let's have a look at some of our actual results now. So let's insert another cut plot. I'm going to use the right plane again, but this time we're going to have a look at the flow velocity. So if I hit OK there, we can see how the fluid velocity varies within the setup. Automatically, this legend is defaulting to the maximum and minimum values present within the flow. And so we can see we've got an almost jet structure forming of the water. We've got a higher mass flow rate, so there's much more fluid flowing there, and hence it's flowing faster. And we can see that the ethanol has a very, very low speed in comparison as it comes up to join the water flow. We'll also see this wake developing behind the sensor. So I'll hide that. I'm just going to generate a couple more to analyse the flow a bit more. But you'll see how truly visual these results are. And this is really important to allow us to properly get an insight into the system. And it's also a nice thing to be able to show to our customers. So here now we can see the velocity distribution, this time in the crosswise direction through the pipe. So we can see how the flow, by the looks of things, the ethanol is shooting up the one side of the pipe. It seems to be sticking to this one side here. We've got less velocity on the outside here, which tells me that perhaps we've got a slightly one-sided flow. This idea sort of continues downstream, and we can see that majority of the high flow speeds are more towards the right-hand side of the screen than the left. And as our system is so symmetric, my thoughts are that probably this flow is going to be fluctuating somewhat, so it's probably going to alternate between the left and the right hand sides. Okay, you'll also see that we have got our peak stresses, our peak velocities impinging on the front of that sensor, which might be incurring some large stresses in the sensor structure itself. So let's now start having a look at what is probably our most important plot values, and that's the ethanol. So here what we're going to do is have a look at how well the ethanol and the water have mixed by plotting the mass fraction of the ethanol. So if we start off with this value at 1, so here we've got 0 at the bottom. You'll see how easy it is to change the values on these plots. So now we can see that at exactly at the inlet of the ethanol, we've got a mass fraction of 1, which is what we would expect. That's solely an inlet of ethanol, but you can see already how the water is flowing into this region and causing it to mix. And then as we move up into the main flow body, we've got regions of ethanol that seem to have formed a pocket across the top, but elsewhere in the flow we've got a fairly low distribution of ethanol. Because of that difference in flow rate, so we've got 10 times more water flow than ethanol, we're looking for a mass flow rate of a mass fraction of ethanol to be about 0.1. So if we change our plot values to a maximum of 0.2, what we can see is that everything above that's red is now above 0.2, which is too high a concentration of ethanol, and everything down here towards the dark blue is too low a concentration of ethanol. Ideally we want it to be slap bang in the middle of that green, so we want the sensor to be shrouded in green. What we can see here is that in actual fact the sensor is in a green portion of the flow, but there is a gradient of mass fraction somewhat near to that sensor, and if the flow is anything like it appears to me to be fluctuating, then we can expect to see that gradient moving up and down and around the sensor and causing those values to fluctuate and be less accurate. So let's have a look at a couple of other plots before we go and move on to analyse our design. One final cut plot we'll use is another mass fraction of ethanol, but in this case we're going to use the front plane, so we get a cross-sectional analysis of the pipe. So as I drag this cut plot through, so you'll see how easily we can move these plots around to view exactly what we're after, you'll see how separated the flow seems to be, and in actual fact at the sensor that previous cut plot was somewhat misleading going through the ideal section of it. We have in actual fact got areas of low and areas of high ethanol concentration also impinging on the sensor, which isn't what we're after. So a couple of other tools that we've got that we can use to analyse the system. I'm just going to cut the body like that so we can select some faces a bit easier. And I'm going to insert a surface plot. And this tool allows us to select a number of faces and plot flow parameters on that surface. So for example, I'm going to plot the mass fraction of ethanol again on the internal faces of this system. And what you'll see is we now get a plot which reflects how that mass fraction is varying exactly at the wall throughout our system. So this is somewhat reflective of the previous cut plots, but now we can see what it's like at the wall and all the way around. So here we can see how there is more ethanol flowing up the one side than there is the other. You'll also notice that we've, as a result of using the surface plot tool, we've got a sort of tube plot now, which might get in the way, you may think, but we can still always change that value by changing the crop region of the plot. So if I change that to 0 and hit OK, you'll see that now we've only got half of that plot, and we can have a look inside still, and it's not going to get in the way of any further plots that we add inside. So let's just hide that, and we'll have a look at a flow trajectory. Flow trajectories are a very, very common used tool in flow simulation CFD, because it's a way of plotting the streamlines, or the flow paths, if you will, of the fluids. So for example, let's grab both the water and the ethanol, and we'll put 50, maybe 100 streamlines in, and I'm going to use lines. You'll see we've got a number of ways of displaying these streamlines, and I'm going to hit OK, and then what the system's going to do is generate those streamlines from each of those inlets. And using the mass fraction, you'll see it looks very, very similar to the cut plots that we've had, but we can use the mass fraction value to paint our streamlines, and we can see how well mixed and how they are mixing here. So we can see how the flow is wrapping up around the top and staying in this pocket in the top section along the inside of the tube until we reach the end, when we're starting to get a little bit more mixing. Okay, another tool we have at our disposal is the particle studies. So this is very similar to the flow trajectories, but instead what we can do is select, so say for this case I'm going to use the ethanol inlet, and we can select, I'll put 50 particles in, and we can select the diameter of these particles. So this is simulating the actual presence of droplets. And I'm just going to grab the ethanol there. So what this is going to do is inject particles of that size and see how they move through the flow. So I'm going to use fairly similar values. So I'm going to use the same mass flow rate that we had specified on the inlet boundary condition. And here we can specify how those particles are treated. So they can either be absorbed when they encounter a wall. We can have them reflect. We can specify reflection parameters, so we can have some absorbed, some reflected, or we can have an ideal reflection where all of the particles that encounter the wall bounce straight back off again. A couple of other physical features, we can include erosion, accretion, and gravity here, and then we can tell the system what information we want out of the study, hit next and hit run. And then what the system's going to do is inject those particles and allow us to review how they move through the system. So here, if I just click play, we can animate how those particles move through the tube. So we can see the particles coming in. You can also see a certain amount of the particles moving downwards, and that's a result of that water flow pushing back down. Then you can see how these particles move, and majority are moving over the top of the sensor and ending up solely at the top half of that outlet lid. So we haven't got many particles coming through to the bottom there. So let's hide that. Next we can use the surface parameters, and we can grab, say for example, I'm just going to select a couple of faces on the sensor here. So I'm going to grab the top and the front face there, and we're going to have a look at the pressure and perhaps the mass fraction of ethanol on that sensor. So if I click show, what the system's going to do is calculate the minimum and the maximum and the average mass fraction values on that sensor surface, and also the pressure. So that pressure we might be able to use in order to work out what forces are acting on the system. We can also see what forces are acting on the system there. But more importantly, we can see that our mass fraction isn't matching up to what it should be. We're looking for that average value to read 0.1 because that's what we want our sensor to read under these flow conditions. Finally, before we go and have a look at some perhaps potential improvements in design, we're going to come in and have a look at using the XY plot tool. And what this allows us to do is, for example, I'm just going to grab an edge there, so I haven't had to sketch anything. By all means you can include a sketch after the solve as well, and I'm just going to use that edge to analyse the mass fraction of ethanol, and I'm going to hit OK. And what the system's going to do now is take the results for a number of nodes that it spans across that edge and output the mass fraction value of ethanol at each of those nodes to Excel, where we get a nice graph showing the variation across that edge, and also we get the numerical values of distance along the edge and the mass fraction of ethanol. Okay, so we've determined now that perhaps our design as it stands isn't really doing what we're after, so we might have to go and make some improvements. So let's go and have a look at studying a slightly different configuration with, I've called it an expander, but essentially it's a bulge in the tube which by my reckoning is going to expand the flow and cause it to diverge and slow down, which should hopefully enable the fluid to mix a bit better. So let's have a look at studying that. Now, to generate the study, we could by all means go back through, use the wizard and try and set up exactly the same settings. But I've already done all that work once, which makes it really easy to do it again. So I'm going to come back to my straight study. So I'm going to come back to my straight analysis, and I'm going to copy the project, or clone the project, and send that setup configuration over to the expander study that hasn't got one already. We'll get a warning that the model is different, so the mesh will need to be changed. So we just agree to that, and now you'll see that we're switched over to the expander study, and we've got the setup exactly as we had it before. The really nice thing that you'll see is we've also got all of our results analysis tools set up exactly as they were before as well. So we can now start to draw direct comparisons between the same plot on different configurations, which means we don't have to go fiddle the legend values or anything like that. We can directly compare to similar designs. So let's have a look at how this design change has improved the situation. So here I've already run the study, and we can have a look at, you'll see I've named all of our results tools as well. So we'll have a look at, say, the velocity from the right hand side, and we'll see that we've still got that water jet structure upstream of the joint, but following from that joint, as we move into the expanded region, you'll see that the flow is significantly slowing down, which is exactly what we're after. That should hopefully have a double effect. One, we are looking for it to generate more mixing, and two, that reduced flow rate in this region, well, not flow rate, but velocity in this region should reduce the pressure force acting on that sensor, and hopefully generate less stress in the stand that's used in there. So the most important thing we're going to have a look at is the mass fraction. So I've got another cut plot of the cross section here, and we're just going to use these arrows again and drag this through. So we can see that upstream the structure is still very separated as we had before, and as we bring that cross section through, we'll see that while I have reduced the flow speed in that area, we haven't actually improved the mixing capabilities of the pipe. In actual fact, this cross-section looks to be worse than it did in the previous design. We've got the sensor sat in a pretty strong yellow band now, which means that we've got a higher concentration of ethanol in this region than we are looking for on the sensor. Again, we should be looking for that value to read 0.1, and hence we want the sensor to be in a nice green region. So let's have a look at some of the other plots that we've generated for this. So here we can see the flow trajectories, so we can see still how the water is flowing back down that ethanol tube, but more importantly we can see how the ethanol is sticking up to this top surface and not interacting too much. We've got a void of red flow trajectories in this bottom area, which tells me that the flow is still sticking to the roof of that section. So by my reckoning, I'm not happy with this design. I'm going to make another change. So let's jump over to my final design and we'll have a look at the changes we've made. So in this case, what I've done is added a little pinch. So we've got exactly the same divergence in the pipe, but I've also added a little pinch which is going to accelerate the flow in that region and hopefully give it a bit more of a mixing action just prior to that divergence, which is still going to slow it down and reduce the flow speed and hence the force that's acting on our sensor. So now let's have a look at that. So first of all, have a look at our velocity. We'll see that we've still got this jet coming through here, and our peak velocity value has increased substantially because we're being accelerated up in this I'm going to call it a nozzle region, but we do still have this slower region, so it's decelerated again in this area of the plot. More importantly, let's have a look at our mass fraction. So we've got the same plot that we've been using so far with 0 and 0.2 at our legend values, and as I drag this plot through, we'll see that upstream, the flow does look very, very similar to what we've had before. As we reach the nozzle, two fluids do still look fairly separated, but because it's been accelerated and now it's being rapidly decelerated, we're getting a significant mixing action, and by the time we reach that sensor, you'll see that that sensor is slap bang in the middle of a nice big green region, which is absolutely ideal. Okay, one tool that we're going to have a look at here, which we didn't see previously, is the ISO surfaces tool. So what this allows us to do is plot a surface at each of these values that we're inputting here. So I'm going to put one at 0.002 below the mass fraction that we're after, and again another one at 0.002 above the mass fraction what we're after. And what this is going to do is generate an envelope in which inside the mass fraction value is plus or minus 0.002 of ethanol. So what you'll see is that our sensor is encased within this envelope, which tells us that we've got a much, much better design, and that sensor will be reading that 0.1 that we are after. Finally, just because it is as with all CFD, it's a very, very visual tool, and that not only enables us to analyse our results properly, but it's a really, really nice thing to be able to show people to illustrate what our design is doing. I've got two particle studies here, so I've injected ethanol and water at each of the separate inlets, and you'll see how nicely we can animate these and see how we've got this mixing action inside here, and how by the end at the outlet we've got a pretty good mixture of both blue and red particles, signifying a nice mixing action within that tube. So let's hide those and finally, one thing that we will briefly have a look at is the parametric study. So while we've improved our design to this point, we may still be looking for our mass fraction value to be more precise. If I have a look at, that's not the one I want, if I have a look at the surface plot on our sensor and select each of these two faces again, we'll use the one for the time being, you'll see that our mass fraction of ethanol is very, very close. It's much closer to that 0.1 that we're after, but we're still not exactly there. So we might want to refine this further, and one way we could do that is simply by varying one of the dimensions, for example the outer diameter of this bulge. And that's very, very easy to do with the flow simulation tool, because we've got this parametric study available to us. So I'm going to select dimension as my parameter type, and I'm going to come in and highlight the sketch for that bulge. I'm going to use that dimension there, so that pulls that dimension in as a variable. I'm going to say that the minimum value is going to be 5 millimeters, and the maximum value is going to be say 15 millimeters. And then hitting next, what we can do is grab a goal. So what I would then be doing is selecting the mass fraction, or the average mass fraction across the top of that surface. I haven't got a goal there this time, but then we could simply add that by selecting it, and then specify what we want. What we want that value to be. So we could say we want that value to be 15 or whatever we're after, and then we can specify the convergence criteria. So we can say if we leave it as 0, it has to be exactly that, or we can say it can be plus or minus 0.01, etc. Then we can specify the number of attempts it has. So the system will carry on trying to refine your design, trying to change that dimension until we reach that value, or until we reach the maximum number of calculations or attempts. And then we can specify whether to generate a new configuration for each of those attempts or not. And then the system will just run through an optimization process and try and give you the best answer that you can get. Okay, finally, I will just bring to your attention another tool that we've got at our disposal, and that's the report tool. Now, this is something that's always really important, especially for CFD and FEA studies, and that's being able to put forward your results and also put forward your setup, so that someone that's looking at your results can check how you've set your study up and verify whether they're happy with what you've done. So I'm just going to right click on the report and go to create, and what that's going to do is bring up the report dialog box. And so I've already got my templates set up, and these are really, really easy to do. It's a case of generating a Word template. So we've got headers and footers and this sort of thing, and also specifying what information we want typically included in the study. And then what the system will do is pick out all of the information that we've asked for in our report and generate that report and bring it up in Microsoft Word. So in a split second, hopefully you'll see Microsoft Word pop up. And there we go. What you'll see is I've got my Innova Systems and SolidWorks headers and footers all set up. I've got our address, and then we've got all the information about the machine I'm using and all of my setup, so the general info, my control planes used for my mesh, etc. All of my fluid setup, all of my gravity and initial conditions, and then finally the results, so all of my goals, all of my parameter values, so we've got maximum and minimum velocities and all of the flow characteristics that you could ever want to include. And we also have the opportunities, so say here I might just want as my front cover a nice picture. So what I can do is activate, say, my flow trajectory of the water, and including a picture is very, very simple. It's just a case of coming over to the pictures and charts, and I'm going to specify that I want the image to be added to the current position in the document, and I just click add report, and that's going to take that snapshot and bring it over into the Microsoft Word document. So it's very easy to swing around and generate as many images as you want to include in the study. Alright, that's about all I've got time for, I'm afraid. So thank you very much for attending. I've got a couple of questions that have been brought to my attention that I'll answer now, but before we get going, just to bring your attention to a couple of webinars that we've got coming up shortly. We've got sheet metal design in SolidWorks, which will be same time next Thursday, so that's Thursday the 10th of May. We've also got what's coming up in and what's available to you in 3D VIA. We've also got using SolidWorks to design mold tools. And as ever, if you want to get in touch, you can drop by our website, which is www.innova-systems.co.uk. You can email us at support@innovasystems.co.uk, or you can give us a call on the number you see on your screen now. So let's have a look at a few of these questions. First one we've got here is, can I save results as videos? The answer is yes, and it's very, very easy. We can, if I close this report tool, we have the animation button available to us. If I select that, we get the standard SolidWorks animation interaction interface, come up on the screen. So then we can use this to animate all of our plots. We can also rotate the model around and zoom in, zoom out, etc., and record that animation for sending off to a customer or just for future reference. What else have we got here? Simultaneous runs. Can you run more than one study at the same time? Again, the answer is yes, thankfully. When I go to click run, we do get this batch results option available to us, and this brings to our attention all of the results, all of the studies, that we've got available to us. So if I want to solve, I can solve that batch run, and what that will do is allow us to either run all of them simultaneously, so we can specify one CPU to each of the studies, or we can run them one after the other. What else have we got? One final one, and then what we'll do is, if you have any further questions, please feel free to drop us an email, and we'll do our best to get back to you as soon as we can with an answer. So I'll just take this one last question, and this is, can I analyse the stress due to the flow? I'm going to assume that you mean, can we analyse the stresses as a result of the forces resulting from our flow study? So, for example, if we switch back to our study here, we've got flow impinging on the front of this sensor, which would be pushing against it. We've got a force generated in the streamwise direction, so we would be getting stresses in the stalk that is holding the sensor up, for example. And the answer is yes. That's very, very easy to do if you've got SolidWorks Simulation or SolidWorks Premium, so the FEA analysis tools that SolidWorks gives. If we come up to the Flow Simulation tab, you'll see that we have the option to export results to simulation, and then it's simply a case of selecting from the simulation menu, include flow results, and all of our flow characteristics will be used in that FEA analysis. Okay, thank you very much for joining me. I'm going to leave you now, but like I said, if you have any further questions, drop us an email and we'll get back to you as soon as we can.